Okay, in the previous lecture, I set up the formalism for calculating the cross section for the process E plus E minus going to mu plus mu minus, and I did the kinematics and phase space integrals to reduce the expression to the stage where the only thing which remains to be calculated is the square of the matrix element. I am going to work it out now, first in the unpolarized case and then in the polarized case, and we will see the various features related to many properties of the Dirac spinors emerging in this calculation. So, first we just have to follow the usual procedure to write down T f I square, and unpolarized case amounts to averaging over the initial state and summing over the final state, averaging over each of the E plus and E minus producing factors of half, and then there is a summation over the all the spin degrees of freedom, and this is the object to be calculated. We easily convert it into the standard form from the expression for T f I, and that gives e raised to 4 by 4 s square. These are all the factors corresponding to the charge, and s square comes from the photon propagator, and then the fermion propagators produce two trace factors, one for the electron line and another for the muon line. So, the electron line, for example, I can insert this index mu for the photon vertex, and then it is P 1 splash plus m e divided by 2 m e for the projection operator of the initial state electron, and then it got contracted with the second factor for the vertex and the projection operator for the initial state positron, which has a p slash minus m structure. So, this is what becomes of the electron line, and then this object has to be multiplied by the corresponding factor coming from the muon line. These are contracted appropriately with the photon indices, and we have to keep track of which index goes to which place. Here the muon is counted as a variable function for v and mu in the final state, but the muon has a wave function u bar, while the electron had a wave function u, and for that reason the projection operators are in different locations, and the corresponding factors looks almost the same, except that the index mu and mu are interchanged. And this is the complete expression for the unpolarized case. We just have to evaluate this traces, which is not at all difficult. By now the procedure has become standard. So, take out various common factors, and the trace produces a overall factor of 4, and then the first trace gives all the dot product in alternating sequence. So, first the mu gets contracted with P, which gives P1 mu P2 nu, then mu gets contracted with nu, the sign flips, so G mu nu P1 dot P2. The third one is P1 mu gets contracted with P2. So, and then there is a contribution corresponding to the mass term, which is minus m square times G mu nu. So, this is the first factor, and the analogous second factor is easily seen to be of the structure which is essentially the same except for the change of labels between electron and muon. And so, that is the result. Now, to calculate it, we have to do the various dot products, and that can be done in a straightforward manner depending on what gets contracted with what. The first we will contract P1 mu P nu with the corresponding P3 P4 terms on the other side. So, it gives P1 dot P3 and P2 dot P4. It occurs twice in the whole cross product, first P1 P2 with 1 mu nu giving the one combination, and when the indices are nu mu, they gives the second combination. So, this term gets an overall factor of 2. This is a similar term which comes from the other cross part, which is gives 2 times P1 dot P4 and P2 dot P3. So, these are all the terms with mu and nu indices sitting on P1 and P2, and then there are contributions from terms which involve G mu nu, which we have to explicitly evaluate as well. So, those terms will involve factors of energy and momenta explicitly. Again, various dot products have to be calculated, and G mu nu contracted with any one of these P1 P mu just produces dot products of those objects, and we just have to work out the overall coefficients of the total term. So, there is a terms which behave like P1 dot P2 multiplied by P3 dot P4, and the it is the plus relative sign and not a product. So, for example, one got P 1 dot P 2 and the other one will produce P 3 dot P 4 when the various things are contracted, and the overall combination has to be calculated. I will just write down the result, and this term has a coefficient minus s and plus there is a overall squared term which gives s square by 4 times 4. Here I have explicitly used the structure that the m square can be converted to s by using the dispersion relation between energy and momenta, and m can be completely eliminated in favor of this overall variable s. So, that is the result, and it can be simplified further to the form where the various dot products can be explicitly evaluated in terms of the angles, and to do that, well, we have to look at the geometry in the center of mass frame, where one can take P 1 and P 2 colliding along one axis, and after that P 3 and P 4 emerging along another axis, and the two sets of directions make an angle theta. So, the dot product between P 1 and P 3 is essentially proportional to cosine theta, and including that factor now explicitly in evaluating the various dot products, the result reduces to the structure the s by 4 minus m square is nothing but the 3 momentum square, and similar for the factor for mu, which accompanies an overall angular dependence cos square theta, and then there is little term left over for the masses. And so, this is the completely simplified form in terms of the energy and the scattering angle and the masses. Everything else has been eliminated from the calculation by choosing the specific center of mass frame, as well as the dispersion relations for both electrons and muons. So, then we have the complete result for the unpolarized cross section, which can be now written in a simple enough form. There is e to the 4 and there are factors of 16 pi square in the denominator, which can be just written as alpha square. Alpha is the fine structure constant, the masses in the overall proportionality actually completely cancel out, and one is left with this factor of alpha square by s cube. Then there is a proportionality constant involving the momenta of the muon and the electron, and that can be written in a form which involves the energy and the masses, and this is a ratio of the muon momentum to the electron momentum. And then there is this overall factor which we calculated above. It can be written in a little different form, but it is the same thing. So, it is s square by 4 plus s times m e square plus m mu square plus 4 cos square theta and these are the factors of the moment of electron and muon. So, this is the expression in full detail. It is convenient to look at various limits of this expression where the result looks simpler, and I can do those things one by one. So, in the high energy limit, which specifically means that the total energy is much larger than the masses, and actually muon mass is much larger than the electron mass anyway. So, it is good to keep the muon in the calculation, but drop the electron mass altogether to a very good approximation whenever the energy is larger than 2 mu to be able to produce muon pair in the annihilation process. So, in that particular case, the cross section is approximately alpha square by s cube. We will drop the electron mass altogether, but keep the muon mass around. So, and this can be further simplified if one decides to neglect the muon mass as well. So, then it just becomes a simple number, and essentially the cosine square theta factors are the only thing which comes out. So, it will becomes alpha square divided by 2 s, and then there is s square by 2 which came out and cancelled this overall factors, and the answer is just 1 plus cos square theta. Sorry, the factor is 4. Okay, so this is a simplified form and it's shows a very simple angular dependence 1 plus cosine square theta, and the overall magnitude is just 1 over the total center of mass energy multiplied by the fine structure constant square. So, this is the result. One can go further and calculate what is the total cross section by integrating out over the angle again. First just neglecting the electron mass and then we will remove the muon mass as well. So, the first step is just alpha square by s cube square root of 1 minus mu square, then the angular integrals over the angle phi just produces 2 pi, and the angle over cosine theta will change the various normalization to two in case here, and here this number will be 2/3. And which can be written as 4 pi alpha square by 3 s cube this factor, and then inside there is 1 plus 2 mu square by s, and well, the result for root s becoming much larger than 2 mu is rather trivial. It is again I cancelled some factors, there is no cube here. Everything else drops out. So, this is the contribution from this various integrals, and one can see the various factors emerging. What experimentally is observed is not this muon thing, but the same process every time the energy of the E plus E minus collider becomes large enough to produce a new pair of particles. So, every time the threshold for a production cross, you will get the corresponding addition to that cross section, and so the cross section just keeps on increasing with steps occurring whenever s, or rather root s, crosses 2 times the mass of a new particle, and that result is often expressed in terms of a ratio which is denoted as R. So, and generically this is just labeled as a FF bar pair, and experimentally it is much easier to compare the contribution of the new pair to the standardized calculation of mu plus mu minus production which we calculated, and this is the object where all the overall factors of various numbers and energy cancel out, and the result looks quite simple. One, there is a factor of the corresponding charge of the new fermion. It does not have to be the same as the muon charge. Muon charge happens to be 1. We will ignore the muon mass in this particular case, and because F is going to be still heavier than muon, and so the overall factor just becomes this numerical constant. There is a slow correction of this m square by s to the constant 1, but much more important is this square root rise which starts at 0 when s is equal to 4 m f square. Below that energy the particle cannot be produced in terms of this pair creation process, and that can be explicitly included by putting a step function. And the square root rise is a kind of characteristic signature which shows that that kind of increase in the cross section is a signature that the new particle is going to be created, and then one can go and look for the specific properties of that particular particle. But this is the first signal which can be easily seen in experimental data, and there can be extra factors in R for other degrees of freedom which we have not included in the calculation, but may be there in real process. For example, there is a factor of 3 for number of quark colors. So, when a quark gets produced, it can be produced in any one of the 3 color, and we have to sum over the possibility. So, R is actually larger by a factor of 3 compared to this formula in case of quarks, and that can be easily included, and what can be then seen is a successive steps in case of hadrons. So, for example, R S for E plus E minus going to hadrons shows steps for production of each new quark flavor as square root of S increases. And the lowest hadrons are all very light, and there you can't separate them easily between the various processes, and most of the time the up, down and strange quarks get produced all together, but then one sees for heavier quarks there is a threshold for production of charm hadrons, and after that there is another threshold for production of bottom hadrons, and the easiest way to see the various signatures, including the value for the degrees of freedom parameterized by number of colors as well as the value of the electric charge, one can easily measure the height of this step and see what the process contributes. So, this is as much as one can say about this behavior of this high energy cross section. One can analyze the behavior near the threshold itself. So, for root O's close to okay, again take the complete expression. The electron mass is still negligible, but we will keep the muon mass finite and see what happens. And in this particular case, S root S is roughly equal to 2 m mu. We can choose, and this corresponds to non-relativistic muons, and then the cross section can be simplified to this differential cross section, which is alpha square by 2s. The 2s comes from combining the overall factor with the remaining dependencies of the matrix element. The dominant factor is this square root, which rises from 0 at s equal to 4 m mu square to 1 when s becomes very large, and there is an other factor of s square by 4, which I have already cancelled with the overall factor outside to produce this result. and the angular dependence, explicitly the cosine square theta term, had a factor of s by 4 m minus m mu square, and that factor basically becomes 0 in this particular case. So, this is actually all that remains of the cross section, and which can be rewritten as alpha square by 2 s. What is there is nothing but the ratio of the momentum of the muon to the energy of the muon, and this is a rather special result. In particular, one can easily see that because the angle dependence has cancelled out, this is a isotropic cross section, and so in this limit pair production is in S wave, and generically if you remember the non-relativistic scattering theory in quantum mechanics, the cross section behavior goes like momentum raised to power 2 L plus 1. In this case, L is equal to 0, and this is just proportional to the magnitude of the momentum, and that is all which appears. One can observe some spatial features which lead to this isotropic behavior. If one can just look at the actual matrix and elements involved, and in this case the current has a particular structure which becomes very obvious. This has only non-zero contribution from the space components, which involve the spin, the result being that u and v are the upper and the lower components of the spinors, and the matrix gamma 0 couples only the diagonal parts. So, it cannot couple this off diagonal u to v connection. We have to include this vector matrices alpha or gamma, and they will only give the non-zero contribution, and the other part is 0. And in particular, it has, if you now look at this particular structure, it has no angular dependence, and therefore, no angular momentum. And so, all which is involved is the spin degree of freedom. The space part has no appearance in this structure at all, and so the cross section is completely isotropic. The spin part is completely dictated by then the conservation of total angular momentum, and so that implies that the spins carried by these muons they have to be aligned with the angular momentum of the initial electrons and positrons. The electrons and positrons are highly relativistic, so all they contribute are actually helicities and not the total angular momentum. We have been dropping the expression for mass of the electron everywhere, or rather treating them as massless. So, the spins of mu plus and mu minus add up to an angular momentum, which has to be the same as the angular momentum provided by the electron, but the electrons have only helicities, which is directed along their initial direction of collision. So, the mu plus and mu minus, even though they are emitted isotropically, their spins are along the electron and E plus E minus collision directions. So, aligned with E plus E minus helicities which is the collision direction. So, this is the result in the non-relativistic case. One can work out the details in a simple manner. We can work out some more details in the non-relativistic case. In particular, bound states can appear because the particle and antiparticle actually can produce bound states analogous to positronium in case of E plus and E minus, but that is little more technical, and I will discuss the bound state problem in the next lecture. Right now, let me go to the another possibility which is allowed in this particular E plus E minus collisions, and that is having the beams E plus and E minus polarized in specific directions, and then we can worry about what will happen to the different possibilities where the E plus and E minus have the same polarization, opposite polarization. One can be called left and right, and so on and so forth. And of course, if one adds up all the different pieces, one must get back the total unpolarized cross sections anyway. So, we have a total check, but in this particular case I can illustrate how to include the polarization factors as well, and we have seen the machinery to do that. So, the factors needed to project along polarization directions are one plus gamma phi S slash by 2 in the Dirac trace for the polarization direction S mu. This projection operator we worked out in the Dirac basis. It is little more convenient to work not in the Dirac basis, but what is the helicity basis or the Weil basis, in which case the projection operators for helicity are 1 plus or minus gamma phi by 2. Just simplifies the calculation a little bit, because the S is cleverly taken along a direction of motion and one does not have to do too complicated calculation. And I am going to denote these factors 1 plus gamma phi by 2 to something which is a right handed helicity, and 1 minus gamma phi by 2 be denoted by the left handed helicity. So, we have the two helicities. We again have the particle and antiparticle degrees of freedom on top of this, and those will make up the 4 complete components. But now, in doing the calculation, we will project both by this energy projection operators, which give p slash plus or minus m divided by 2 m, as well as the helicity projection operators, which will now be 1 plus or minus gamma phi by 2. Okay. Now, the interesting point is to look at this structure of the interaction which we have in the helicity basis, and the typical objects are the currents. So, and the non-zero contribution comes only when the spinors in the current are of the same type. The reason being that there are the structures, for example, V bar, gamma mu, u, which can be written as V dagger, gamma 0, gamma mu, u, and one wants to introduce these factors of the same type because the gamma phi is going to anticommute with both gamma 0 and gamma mu. And so, if there is a 1 plus gamma phi by 2 operating on u, it again has to be 1 plus gamma phi by 2 operating on v. There is no other choice allowed. If they are of opposite, once you commute through gamma 0 and gamma mu, they will annihilate. So, for example, V dagger 1 plus gamma by 2 So, this restricts the helicity states which can contribute to this current, and the current is the basic part of the matrix element, and so only one combination of the helicity can contribute, the other one does not. And what we have chosen as the convention that the helicity of positron is opposite to the corresponding projection operator for this wave function v. This was our convention between mapping of a particle and a antiparticle. The v is a negative energy solution, and the conversion from the particle to antiparticle language flips everything, momentum, position, as well as the helicity. We have seen this and rather built it into our convention. So, the whole reaction, so the process occurs only when E plus and E minus have opposite helicities or in the center of mass frame they are moving in opposite directions. So, the spin becomes the same for both these particles, and so the state which contributes, actually if you measure the angular momentum along the direction of collisions. So, the angular momentum along direction of collision is 1. Both the contributions of half add up, and this is a structure directly dictated by the relativistic spinor definitions. One can actually see it in different ways, and one way is to just go and look at the representations which we have in the Lorentz group language. The objects which we have are two Weil spinors u and v, both of them have the same projection structure. So, when you combine these two, you get the states. Well, this is a tensor product, and the simple angular momentum addition rules says that this gives these two states. One of them is a helicity 1 object, another is a total scalar part, and what is contributing in this process is the helicity 1 part, and the other component which has the same combinations, but not the same helicity. If you do half 0 tensor product with 0 half, you will get this contribution half half, which is a vector representation. And that is absent in this particular scenario, and so we do not get the combinations where the spins are pointing in opposite direction for E plus and E minus. Now, the same property is also true for the muons in the final state. It has the same structures and the same transformation properties under Lorentz group. So, they obey the same result, and so now we will look at this various combinations allowed by this helicity selection rule one by one next time.